right, so say you got a circuit that looks like this, and you want to know how much current goes through each of these resistors. Well, you could certainly figure out the equivalent resistance and then use Ohm's law to do it, but you can also use Kirchhoff's circuit rules. And so Kirchhoff came up with these rules, which are actually basically conservation of charge and conservation of energy, but they will let you know what's going on in a circuit. And it can actually be any circuit. It just doesn't have to be one with just resistors. You can do it with resistors, capacitors, transistors, whatever you want. The circuit rules still work. Okay, so what are they? There are two rules. First, you got the junction rule. And the junction rule says current that goes into a junction equals current that comes out a junction. So what is a junction? Well, a junction is anywhere that a bunch of wires meet. So like that right there is a junction. You got 3 wires that all come and meet up right here. This guy right here, also a junction. You got 3 wires coming in, they're meeting up and joining. This here, not a junction, because actually just one wire. It comes down and then it turns 90 degrees. But there's only one wire here, not a bunch of wires meeting. So the junction rule. And I claim the junction rule is actually just conservation of charge. And I'm going to leave it for you to think about why that should be so. If you think about all the current that's going in to a junction has to equal all the current coming out. We can write this a little more succinctly as the sum of all the current into a junction equals the sum of all the current that's coming out of a junction. So that's the junction rule. Okay, I rewrote the junction rule more neatly and in a prettier color. Next rule is the loop rule. And the loop rule says the potential difference, the total potential difference as you go around a loop has to add up to 0. So basically, if you walk around a loop, which is any path that you travel around the wires in a circuit and across the elements and end up in the same place. So like here's a loop. This guy's also a loop over here. You can go one loop all the way on the outside. Those are all loops. So as you travel a loop and you look at how much voltage you gain on a battery, how much you lose across a resistor, lose across a second resistor, all of those gains and losses have to cancel each other out. So once you get back to where you started, you end up at the same potential you began at. So the difference from start to end is 0. And this guy turns out to be the same as conservation of energy. And again, I'm going to let you think about why the fact that as you look at the potential all the way around a loop, that has to add up to 0 is the same thing as conservation of energy. And I'm just going to remind you, if you want to know the potential energy for electric potential, well, that's going to be the charge of the little current, free charges that are running around in the current, times the potential. So there's a really close connection between potential and energy. And we can write this a little more succinctly as if you add up all the voltages in your loop, they've got to add up to 0. All right, so applying them, how do we do this? All right, so first thing is find your junctions. Two, name the currents, by which I mean just give them a symbol in the same way we've given the voltage across the terminal of these two batteries. We've called it V sub T, or the resistance of this first resistor, we've called it R1. So name the currents and guess the directions. So current has to flow either kind of this way or that way along the wire, and so we just need to guess, and it'll actually, our math will tell us if we've guessed right or not. You just have to be consistent and follow the sign conventions that I'll talk about in a minute. All right, and then once you've done that, then you apply the junction rule, this guy, and you apply it -1, and I'll talk about what that means in a little bit. So first, let's find the junctions. We got one junction here, I'll call that junction A. We got another junction there, we call that junction B, so we got 2 junctions. Now we gotta name our currents and guess their directions. So we're gonna have current that's gonna travel from B through the battery, through resistor 1 to A. I'm gonna call that current 1 because it's going through resistor 1. And I'm gonna guess it's going to be traveling this way. So if it travels towards A through resistor 1, that's when it's going to also be going up through the battery here, and it's going to be going from B towards the battery there. So I have guessed this current travels this way, and I'm going to call it current 1. Current 2, I'm going to call that will be the current that goes through resistor 2, and I'm going to guess it goes down like this. And I know that has to be a new current. Every time you hit a junction, you have to switch currents because how much current comes in on one, it might be a different amount that comes down here because that has a choice. It can come in and go this way or it can go that way. So current 1, as long as things are in series, it's the same current. But as soon as you get a choice at a junction, you'd have to switch over to a new current name. And then the final current is the one that goes through resistor 3. I'm going to guess it's going to go that way, towards A through resistor 3. And then if it's going that way, that means it's going to come out in this direction, and then it's going to go up that way. And again, all of these currents are the same current because this all is in series. It has no choice until it gets to the junction. All right, so I've named my currents and I've guessed their direction. I've guessed 1 goes this way, 2 goes that way, and then 3 goes out that way. Now I'm going to apply the junction rule -1. And what the -1 means that I've got 2 junctions. I need to apply the junction rule for the 2 junctions -1. So I really only need to apply it once. So let's see why. So let's start with A. All right, for junction A, the currents that are going into junction A are current 1 and current 3. Those are the 2 that are coming in and hitting with junction A. And the current that's going out is just junction 2. Sorry, it's just current 2. So that's what happens at junction 1. Currents 1 and 3 go in, current 2 goes out. Now let's look at junction B. Here I've only got current 2 comes in. So 2 goes in, and then 1 and 3 goes out. And now that we've done this, you can see why we need one less equation than we have junctions, because these 2 equations are exactly the same equation. Current 1 plus current 3 equals current 2. And here we just switched how we've written. Current 2 is current 1 plus current 3. So we don't even need this one. All right, so that takes care of the junction rules. Next, the loop rule. Okay, so here are my rules. Here I've applied the junction rule. I had 2 junctions, so I got 1 equation. Next, to do the loop rule, first thing I need to do is find the loops. And then after that, I can apply the loop rule. And again, I need to do it for the number of loops I've got -1. So here I have 3 loops, and that means I'll need 2 equations to come out of it, because the third one will just be redundant. So the first loop I'm going to do is going to be this loop here over on the left, and then I will do a loop like that on the right, and the third loop would be the one that goes all the way around on the outside. This guy, that would be loop 3, but I'm not going to use it because I got 3 loops, and so I only need 2 equations. Okay, so let's go ahead and apply for loop 1 first. So for loop number 1, I'm going to go over the battery. So I'll need the voltage difference across the battery, and then over resistor 1. So I'm going to call that voltage 1. That's the voltage difference across resistor 1, and then over resistor 2. So I'll call that voltage 2. And then I'm back where I started, and all my voltages are adding up to 0. Now here's where the sign conventions come in, so let's talk about those. Alright, so for the sign conventions, for resistors, now remember from Ohm's law, the voltage across a resistor is equal to the current times the resistance. For a resistor, if you go with the current on your loop, then the voltage across that resistor is going to be a voltage drop. So you're going to lose voltage. So let's take a look at what I did on voltage 1. When I went across resistor 1, I went in the direction my current was. So I lost voltage as I went across this resistor. As I went across resistor 2, my loop went down here, and my current's also going down. So I'm going to lose voltage here, and it's going to be a voltage drop. If you went against the current, you'd have a voltage gain. So that would be positive IR. So with the current, you have a drop. If you go against the current, which is kind of the wrong way across the resistor, you get a gain. For both of mine, I've gone with the current as I've guessed the direction it's going, so I get a negative sign there. So filling in what I know, I have the voltage T, the terminal voltage of the battery, minus, because I'm going with the current on resistor 1, and I need current 1 times R1. That's the voltage drop across this resistor. Then here, as I come down on this side of the loop, I'm going across resistor 2 with current 2, and I'm traveling in the direction, so that is another voltage drop. So minus I2 R2, that equals 0. So that is my loop equation for this first loop. For the second loop, this guy, I go up on this side, this way, and then down. So here, when I travel up, I'm going opposite the direction of my current. So, get my voltages in first. So first voltage drop, and then my second voltage drop across resistor 3. So voltage drop across 2, voltage drop across 3, wire, no voltage drop, back where I started, 0. Okay, so voltage drop across 2, I'm going the wrong way. So I have a voltage gain, positive here, because I'm going against the current on my loop. I2 R2 is the voltage drop across that resistor. And I'm going the wrong way against what I've guessed current 3 is going. So that's another voltage gain. I3 R3, that's my second. All right, so I've got 3 equations, 1, 2, 3. I have a third loop. I could go all the way around, but that equation wouldn't actually give me any information that's not in these 2 equations already. So that's the figure out all your loops and then apply the loop rule -1 for one less loop than you actually have. All right, and there's one more sign convention to talk about, and this is for EMF sources, so our batteries. If you go the correct way across a battery, that is, you're going from the negative terminal to the positive terminal, so negative to positive, you have a voltage gain, and that means you're going to use the plus sign. I've gained voltages as I walk that way in my loop. So that's what I did here. I went the right way across the battery, so my V was positive. If I go the wrong way, that is, I go down like this, if I went from the positive to the negative terminal on my battery, then I've had a voltage loss. I'd be going down in potential if you go the wrong way across a battery, and so then I'd have to use a negative sign here. So if my loop 1 actually circled the other way, that terminal voltage would have to be negative because I'm going the wrong way across the battery. So as long as you follow those, the signs will all work out. All right, so here are my 3 equations. And you'll notice I know what the terminal voltage is. It's 2 volts. I know what resistor 1 is. It's 1 ohm. I know what resistor 2 is. It's 2 ohms. I know what resistor 3 is. It's 3 ohms. The only things I don't know are currents 1, 2, and 3. So there are 3 things I don't know, and I have 3 equations, and that's a system of equations that I can solve fully. So if at this point you're pretty confident you can do the algebra, you can just go ahead and skip to the end of the video and see if you get the same answers as I do. If you want to watch me do this, then keep watching and we'll do it together. Alright, I'm going to start with this equation, and I'm going to get current 3 in terms of current 2. So I've got current 2 here times resistor 2. I'm going to move this term to the other side of the equation. So that'll be negative I3 R3. And now I'm going to plug in what I know about the resistors. R2 is 2 ohms. So I2 is 2 ohms. And R2 or R3 is 3 ohms. So I can now just divide negative 3 ohms on both sides of the equation. My ohms cancel, the 3 and the negative cancel here, and I will get current 3 is negative 2/3 current 2. Okay, so now if I find current 2, I know current 3. Next up, I'm going to take this equation and now plug in what I know about current 3 to find current 1 in terms of current 2. So I know current 3 has this relationship to current 2, so I'm going to plug that in. Instead of I3, I'll plug in negative 2/3 current 2. Now I'm going to solve this, move this term over on the other side. I got I1 is current 2 plus 2/3 current 2. And so if I add these together, well, I got 1 plus 2/3. That gives me 5/3 current 2. So current 1 equals 5/3 current 2. So now if I find current 2, I also know current 1. I've used this equation to get that. I've used this and that equation to get this. So I've got this equation left. And I'm just going to move these two guys with the resistance and the current over to the other side of the equation. Oops, erased a bit of my equation there. Let me fill it back in. And I have the terminal voltage of the battery. I'm going to move this to the other side of the equation, equals I1 R1. I'm going to move this term also to the other side, so that equals I2 R2. My terminal voltage is 2 volts, so I can plug that in, 2 volts here. I1, well, I've got that in terms of I2, so let me plug that in. 5/3 I2. R1 is 1 ohm. I2, well, I don't know that one yet, but R2 is 2 ohms. Okay, and now let's combine all of this. I got 1 ohm times 5/3 and 2 ohms times nothing over here. So 2 volts equals 5/3 ohm I2 plus 2, which is the same as 6/3 of an ohm I2. So I can go ahead and combine this. I'm going to erase this and then rewrite it because I've run out of space. Alright, so 2 volts, that's this, 5/3 ohms I2 plus 6/3 ohms I2, that's going to be 11/3 ohms I2. I'm going to divide by 11/3 ohms, so I will have over here 2 volts divided by, I guess we'll multiply by 3, divide by 11 ohms here, equals I2. So I just divided by 11/3 ohms over here, and the 3 came up because I was dividing, 11 came down because it was multiplying over here. And we'll just clean this up a little bit. 3 times 2 is 6. 11ths volts over ohms is amps. So current 2, which is the current through resistor 2, is 11/6 amps. And since it's positive here, that means I guess the correct direction here. So I2 really is traveling down in this fashion through resistor 2. Now I can find the other two currents. I3 is negative 2/3 I2, so I'm going to go ahead and plug that in. 6/11 amps. So I3 is 2 times 6, or let's go ahead and do that, is negative 2 times 6 is 12. 3 times 11 is 33. So I3 is negative 1233 amps, and the negative means I guessed wrong on the direction of the current. Instead of the current traveling towards this junction, it's actually traveling away. So the current comes up through the battery and then it goes down or out that way. So current 3 guessed wrong, but it just came out as a negative here to let me know I did that. All right, now let's figure out what current 1 is. It is 5/3 of current 2. So I'm going to plug in for current 2. There we go, and so I will get 5 times 6 is 30, 3 times 11 is 33 amps. So current 2 is 3 over 33 amps, or if we simplify it a bit, 10 over 11 amps. So those are all the currents going through. So there we go. Now we've solved. We know exactly how much current is going through each of these resistors. It was kind of a mess. Through resistor 2, that's the current. Through resistor 1, that's the current. And through resistor 3, that's the current with the negative sign telling us I guessed wrong. This current 3 is actually traveling the other way. So out like this and then down like this. And that's how you use Kirchhoff's circuit rules.